We wish to acknowledge that the land on which the Fields Institute operates, it's for thousands of years, has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. And the speaker today is Peng, who's a PhD student majoring in statistics at Simon Fraser University. Ken's research interests are in biostatistics, Bayesian statistics, and sports analytics. I like the sports analytics. He is currently working on some wastewater COVID-19 related research with Charmaine Dean at the University of Waterloo. And we are all very excited about the wastewater research. This stuff is really cool. So I turn it over to Ken and we'll hear your speech today.
Okay, thanks for the introduction, Ben. I'm going to share my screen. Can you see my screen? Is that a full screen?
Looks good.
Okay, great. Good afternoon, everyone, and good morning to those who are at Pacific time, like myself. I'm very excited to have this opportunity to give this presentation here. And the title of my presentation is going to be an exploration of the relationship between wastewater viral signals and COVID-19 hospitalizations in Ottawa, Ontario. And this is a joint work with Dr. Elizabeth Runoff and Dr. Charmaine Dean from University of Waterloo, and also Dr. John Hu from Simon Fraser University. And I will start with the outline of my presentation. So I'm first going to introduce some background of the wastewater surveillance data. Then I'm going to describe what kind of data we have. And our analysis has two parts, the correlation analysis and the nonlinear model with random time lag. And lastly, I'm going to summarize our project and have the discussion section. So let's start with some background knowledge about the wastewater surveillance data. So this kind of data has have been used previously for monitoring a wide range of behavioral, socioeconomic, and biological markers. And the SARS-CoV-2, the virus which causing the COVID-19, is excreted in the feces of infected individuals and can be detected in the wastewater. And the viral signal is being detected in the wastewater surveillance system using a technique called RT-PCR technique. So basically, there are two kinds of genes which can be used to detect the SARS-CoV-2, and they are called N1 and N2 genes. And basically, the viral signal try to detect the concentration of the N1 and N2 gene within the wastewater surveillance system. And here in this page, I list the map of the global SARS-CoV-2 wastewater surveillance effort. So there are a lot of wastewater surveillance sites over the world. And from this map, at the moment when do the screenshot, you can see there are more than 3,000 sites of the wastewater surveillance sites. And there are over 100 dashboards are provided. However, not all of them has the data available. And actually to obtain the wastewater surveillance data is not so straightforward, but very lucky the Ottawa provide a very detailed wastewater surveillance data, which we will use in the project. And if you are interested in this map, the link is given here. And here are some previous applications of the wastewater surveillance data. So it has been used to monitor the regional and community drug abuse and industrial pollutant chemicals, and also polioviruses in the global polio eradication initiative. And during the COVID-19, the wastewater surveillance data has been drawing people's attention. And a lot of researchers has been considered the wastewater surveillance data as a useful tool to monitor the COVID-19 pandemic. Garland's paper discussed the possibility to use wastewater viral signals to predict COVID-19 epidemiological data. And time lag correlation confirmed wastewater-based epidemiology predicts new COVID cases and hospitalizations. So what is the time lag correlation? So imagine if people get infected and these people will produce the viral signal like very quickly. However, these people will be detected and admitted to the hospital after a few days. Therefore, there is a time delay between the infected individual produce the viral signal and infected people contributes to the cases number and hospitalization numbers. Therefore, the distributed lag model has been considered as a useful tool to explore the relationship between wastewater viral signals and COVID-19 epidemiology. So in our project, the data is obtained from this GitHub link, and it's public available, and it contains the Ottawa's surveillance data. So one thing special for Ottawa is that Ottawa only has one wastewater surveillance site. Usually other big cities has multiple sites. However, the Ottawa only has one wastewater surveillance site to support the whole Ottawa. And the copies of the N1 and N2 genes are normalized using another virus called this PMMOV. So the proposal to do this is to remove the seasonal effect and the weather effect to the viral concentration. So imagine if it's raining, then the water level in the wastewater system is going to increase. So the concentration of the virus is going to decrease. Therefore, people use this another virus to normalize the N1 and N2 gene, because this virus is also found in the human feces. And by doing that, we obtain a thing called wastewater viral signals. And detailed about this method can be found at their data dashboard. And in this project, the average of N1 and N2 gene is considered because they are actually measuring a sampling the viral load. And in this plot, I just briefly summary how the wastewater surveillance data works. So the people get infected, and this infected individual will produce the viral signal to the serum catchment area. Then the serum catchment area goes to the wastewater surveillance site, and the wastewater scientists obtain some samples from the sampling site and bring it back to the lab and use the technique I mentioned before to detect the concentration of the N1 and N2 gene. And then by doing some calculation using another virus I mentioned before to calculate the viral signals. And that's everything about the background of the wastewater surveillance data. And in this project, we focus on the COVID-19 related hospitalizations. And in this page, I just briefly mentioned where we obtain data. So the data of the hospitalizations at Ottawa is also public available and can be taken from Open Ottawa dataset, which is at this link. So a good thing for Ottawa is that Ottawa only has one wastewater surveillance site, also has only one record of the hospitalizations, which support the whole Ottawa. Therefore, our data are quite simple. It's just two time series. One represents the wastewater viral signals, and another one is the COVID-19 related hospitalizations. So in this page, I show the visualization of the data and do some preliminary analysis. So in the plot here, I'm showing the time series of the 7 days moving average of wastewater viral signals and the COVID-19 hospitalizations. So firstly, we can observe that there is strong association between those two time series. The wastewater viral signal can overall capture the trend of the hospitalization. Also, we can notice there is a delay between the viral signal and hospitalizations. So although it's not that obvious, however, you can still see usually the viral signal changes first, then the hospitalization follows. However, this association is not may not be linear and may vary across different waves. For example, if we look at the periods between July 2021 and December 2021, you can see the orange line is not aligning well with the blue area. So that's the Delta wave. And the reason might be caused by the population immunity from the vaccination, because at that period, the first 2 doses has reached a very high coverage proportion. And another noticeable period is Omicron BA.1 wave, which is around January 2022. We can see there is a small wave of the wastewater viral signals. However, there are a lot of hospitalizations. And later on the BA.2 wave, the thing changed. The wastewater viral signal was very high. However, there are only a few hospitalizations. So we believe the relationship between the hospitalization and the viral signal may vary across time and may not be linear. Therefore, we perform our analysis. And the goal of the project is to enhance the understanding of the nonlinear and time-varying relationship between the wastewater viral signals and COVID-19 hospitalizations. So the first part of our analysis is very simple, the correlation analysis. Huxley's paper evaluated the spear mass rank correlation between the 5 days and 3 days midpoint average of wastewater viral signal and 5 days midpoint average of COVID-19 epidemiological data, such as positive cases, hospital admissions, ICU admissions, and deaths, with different time lag for each wave. So the first part of our analysis is basically we extended this time step correlation analysis. And I will directly jump to next slides to introduce our method. So we used the idea of the rolling correlation to calculate spear mass correlation with 100 days rolling window. So we calculate the correlation between the moving average of wastewater viral signals and COVID-19 hospitalizations. We let the time tau1 to be the time lag between wastewater viral signals and COVID-19 hospitalizations. And we let tau2 be the time window of the moving average, which is used to smooth out the wastewater viral signals. And for each rolling window, we allow the tau1 and tau2 to vary and check what combination of the tau1 and the tau2 can maximize the correlation between the wastewater viral signals and COVID-19 hospitalizations. And we record the optimized correlation and corresponding combination of tau1 and tau2. So what can be explored by doing this? Firstly, we can investigate the optimized choice of the time lag and the time window of the moving average between the wastewater viral signals and the hospitalizations for each period. And we can also investigate how the correlation and the choice of the tau1 and tau2 varies over time. So to make it more clear, I show an example of the results for first 4 rolling windows. So for each rolling window, that's 100 days, we will have the optimized tau1, optimized tau2, and the corresponding optimized correlation. And in this page, I show the results of this analysis. So firstly, let's look at those 2 plots. The first plot is showing the optimized correlation over time. And the second plot is showing the optimized tau1 plus tau2 over time. So the first thing we can observe is that the correlation and tau1 plus tau2 are varies over time. And we can observe some interesting period, for example, Delta wave. And during the Delta wave, the wastewater viral signal is only weakly correlated with hospitalization. And other period, you can see overall the correlation between COVID-19 hospitalization and wastewater viral signal are pretty high. And we can also see in the current days, the correlation between the viral signal and hospitalization is also decreasing. So as I mentioned before, this might be caused by the population immunity from the vaccination. During the Delta wave, the first 2 doses has reached a very high coverage proportion. And currently, the 3rd dose and the 4th dose are also increasing a lot. And about the TOR1 plus TOR2, we observed some interesting features. So basically, it sometimes get high and then directly decrease very fast in a short period. And we manually checked those days and we found that optimized TOR1 plus TOR2 gets high while the hospitalization increase and gets low while the hospitalization decrease. So this may suggest that when the hospitalization is increasing, it basically the delay between the people produce viral signal and people goes to hospital is like has longer time lag. So since we observe this time varying correlation and we believe it might be caused by the vaccination, therefore we check the vaccination information and see if we can use the vaccination data as a adjusting variable in our modeling analysis. So the vaccination data for Ottawa is also publicly available and can be taken from their data dashboard. So in this plot, I'm directly obtaining the screenshot from their website, and the data looks like this. Sorry. So we have the dose 1, dose 2, dose 3, and dose 4. We have the daily doses of the vaccine received, and from that we can calculate the cumulative number of doses for each dose. So you can see the four lines here are showing the cumulative coverage proportion over time, and they are always increase, and they all have similar shape. So if we consider directly to include those cumulative number of doses into the model analysis, then they are going to be highly correlated. Therefore, without the detailed data, we don't know in our hospitalization data, we only know the count of the hospitalization at each day. We don't know how many of them are vaccinated, how many of them are received 2nd dose or something like that. So we consider a simplified approach based on the findings from previous research to simulate the varying of the vaccination effectiveness against hospitalization under 3 different scenarios. And we use the simulated vaccination effectiveness as the adjusting variable in our model. So I will briefly introduce how 3 different scenarios looks like. So in the scenario 1, we directly use the cumulative number of vaccine doses without any varying. So basically, we just sum up all the vaccine doses. And then the scenario 2 will assume each dose of the vaccine become effectiveness against hospitalization after 1 days is received. And the vaccination effectiveness was 30% per day. So the scenario 1 is just when T1 and theta equal to 0. And in the scenario 2, we assume the T1 and theta follow certain distributions. And in the scenario 3, we assume the further waning during the Omicron period based on the results of the vaccination effectiveness on this paper. So I didn't list all the detail about this simulation because it's quite long. And also our main focus of this project is wastewater viral signal. However, if you are interested, we can discuss this later. And in this page, I just show you how the simulated vaccination effectiveness looks like. So the scenario 1 is just the cumulative number of the vaccination doses. So you can see it always increase. And in the scenario 2, we assume some waning of the vaccination effectiveness against hospitalization. So starts from around Omicron wave, since the daily doses of the vaccine received has being much fewer than before. So you can see the simulated vaccination effectiveness actually starts to become lower during that period. And the scenario 3, we have the further waning during the Omicron period. So basically for the scenario 3, the pre-Omicron period is same as before. And then I will jump to the our model. So before I introduce our model, I want to review 2 simple models. So the first one is distributed lag model. So this model includes lag exposure variable as covariance to predict the response. So basically you use the predictor from today and yesterday and previous days to predict today's response. And the second model is generalized additive model. So this model investigates the nonlinear covariance effects, and it has following form. So basically the link function of the expectation of the response given the predictors is equal to the intercept plus f1 x1, f2 x2. So the f here is the smooth functions, which so each smooth function consists for multiple basis functions. And it's used, the proposal to do is to transform the original x and to investigate the nonlinear effect, nonlinear association between the x and y. And in this project, we use the model called distributed lag nonlinear model. So this model is developed by Gasparini's group in 2010, and it has the following form. So the link function of the expectation of response variable at time t, given the explanatory variable, is equal to intercept plus the following 2 terms. So the third term is simply just a linear combination of the covariance, which has linear effects to the response. And the important part is the second term. The S here is called by the cross basis functions. And it simultaneously describes the association along 2 dimensions. It describes a nonlinear association between 2 dimensions, predictor dimension and lag dimension. So it has following form. So in simple word, so if we think about the generalized additive model, we use a smooth function to transform the original covariance. However, here we use the cross basis function. So basically you transform the original covariance by a set of basis function in a predictor dimension, and then transform it again with another set of basis functions. So it transformed twice, and that's why it's called cross basis function. And to investigate the nonlinear association along 2 directions. And then I just list some previous applications of this model. So it has been used to investigate lag effect of air temperature on hospital admissions of adults, and also the climate variable and nonlinear association between climate variable and hospital divisions, and nonlinear lag association between temperature and mortality. And in our project, we model the wastewater surveillance data with the this distributed lag nonlinear model. And our model can be written as the following form. We use the log link function and the log of expectation of YT given the wastewater data, and the VT star. So VT star is the simulated cumulative vaccination effectiveness I discussed before. And it's equal to the alpha plus F1T and this cross basis function, and the gamma times VT star. So alpha here is a fixed intercept, and F1T is a function of time t, which summarizes the monthly contribution of other factors not included in the model, such as school closed and limited testing. And the VT star here is the adjusted vaccination effectiveness at day t and under 3 different scenarios. And WT is the historical information of wastewater viral signals at day T, we consider the lag range between 0 to 50. So basically, infected individual produce viral signal, and the infected individual goes to the hospital. The time lag between those two things, we consider it's a random number from 0 to 50 for each individual. And we applied this model to Omicron and pre-Omicron period separately, since the thing changed a lot and the virus, the behavior of the virus changed a lot during the Omicron period. So we want to see how the result is different during the Omicron period and pre-Omicron period. And here, I firstly show the some general information about the model results. So first, we found that model was able to capture the trend of the true COVID-19 hospitalizations. And you can see from 3 scenarios and for each period, so for pre-Omicron period and Omicron period, the adjusted R-square are all pretty high, and the gamma, estimated gamma are all significant. And this suggests the effect from the vaccination effectiveness is significant. And in the following 2 plots, I'm showing the black curve is observed hospitalization, and the red curve is the model estimated hospitalization. You can see they are matching. Overall, they match pretty well. And then we want to investigate the nonlinear association between the viral signal and COVID-19 hospitalizations. So the plot I'm showing here is from pre-Omicron period. And for each plot, the y-axis is the relative risk of the hospitalizations. The baseline is there's no wastewater viral signal. And the x-axis is the viral signals. So first plot is showing when the wastewater, when the time lag between the wastewater and the hospitalization is 0. And the second plot is when the lag is at 10. And this plot is when the lag is at 5. And the last plot is when the lag is at 15. So first thing we can observe is that whenever the wastewater viral signal increase, the relative risk of the hospitalization also increase. Their relationship is roughly monotonic. And also, if we look at the pre-Omicron period, we can also observe similar features. When the wastewater viral signal increase, the relative risk of the hospitalization increase. However, during the Omicron period, when the lag is very small, the association between viral signal and COVID-19 hospitalization is not significant. And if we plot the relative risk in another way, so basically right now I'm plotting the x-axis as the time lag, and each plot is representing the association when the wastewater is at certain level. So we can see the in first. I should have a sub label here. Sorry about that. The first in the first column, I'm actually showing the in the first row, I'm actually showing the okay, sorry about that. I do have the title. So this is a pre-Omicron period, and the second row is the Omicron period. So you can see in the pre-Omicron period, the relative risk is at a high level when the lag is small, and then it decreases a little bit. However, it's quite flat, but it's still, you can see a little bit decrease, and then increase while the time lag becomes larger. However, in the Omicron period, it's quite different. The relative risk is not significant when the lag is very small. And it increased first, and it reached the highest level around 9 days. Then it decreased again, become not significant that the lag equal to 50. So in this page, I show the 3D plot to better see how they are associated. So the first plot is the nonlinear lag association between viral signal and hospitalization and pre-Omicron period. And the second plot is the Omicron period. So we can see if we look at it from this side, it always, the wastewater viral signal increase, the hospitalization increase, no matter the pre-Omicron period or Omicron period. However, if we look at it from the time lag side, we can see the pre-Omicron period is different compared to Omicron period, because the pre-Omicron period, the relative risk can increase. However, in the Omicron period, it's reached the highest level around 9 days after the wastewater viral signal changes. And that's all the results I want to share with you. And then I will briefly summarize our project and summarize some limitation of the current work. So we investigated time lag between the COVID-19 hospitalizations and the wastewater viral signals by doing the rolling correlation analysis. And we investigated nonlinear association between COVID-19 hospitalizations and wastewater viral signal using the nonlinear model with random lag. And the monotonic relationship between wastewater viral signal confirmed that the wastewater viral signals can be used as a marker of the increases in the hospitalization. Also, we have some limitations. Our data are quite simple right now. Don't contain the variance of concern in wastewater surveillance data, and we don't have the detailed information about the hospitalization, such as age, vaccine status, those things. And I'm mentioning the variance of concern in wastewater surveillance data here because I think it should be available, because in their data dashboard, we can see some visualizations about the proportion of each variance. However, the data is not publicly available. And that's everything about my presentation, and thanks for your attention. And I look forward to your questions. And I saw some in the chat. Oh, is there some problem with my slides?
No, Dr. Ern was just asking for access to your slides and the paper, okay, maybe after the meeting.
Yeah, sure. I'll be happy to share it.
So anybody who has a question, feel free to use the